Learn like a pro.
Have you ever wondered how scientists can understand something that happens in a flash, like an explosion, but also something that takes centuries, like a mountain eroding? Well, it all boils down to one thing: measuring the speed of chemistry. And today, we're going to step into our virtual lab to see exactly how we can put a stopwatch on a chemical reaction.
I mean, just think about it for a second. On one hand, you've got sodium hitting water and boom, it's an almost instant violent reaction. But on the other hand, you have iron slowly turning to rust over years, or a giant rock weathering away over thousands of years. The chemistry is there in both, but the speed, the reaction rate, is just worlds apart. And that rate is what we're going to dive into today.
So, here's our game plan. First, we'll get a solid definition for reaction rate. Then, we're going to get our hands dirty in the virtual lab and see how to measure reactions that make gas. After that, we'll look at how to read the story a graph tells us, figure out what to do when there's no gas to measure, and finally, we'll connect it all back to why this is so important in the real world.
All right, first things first. We can't just say a reaction is fast or slow. We need to get specific. How do we actually put a number on chemical speed?
You know, at its heart, it's a pretty simple idea. The rate of reaction is really just a measure of how quickly our starting ingredients, the reactants, are turning into the stuff we end up with, the products. It's all about tracking change over time.
And this right here is absolutely key. It's a simple but super powerful relationship. If a reaction happens in the blink of an eye, the time it takes is incredibly short. If a reaction drags on forever, the time is incredibly long. So as one goes up, the other goes down. They're inversely proportional.
Okay, so that's the theory. But let's get practical. Let's head into our virtual lab, because seeing how this is actually done is way more interesting, especially for reactions that produce a gas, which happens all the time in chemistry.
So we've got two main tricks up our sleeve here. We can either measure how much mass is lost as a gas escapes, or we can just trap that gas and measure its volume directly. Let's check out the setup for both.
So method number one is just beautifully simple. It relies on a basic law of physics. Matter doesn't just vanish. So, if your reaction creates a gas and that gas floats away, the total mass of your setup has to go down. And get this, the amount of mass you lose is the exact mass of the gas that escaped. Pretty clever, right?
The setup for this is so straightforward. You just mix your reactants in a flask. Then you put a little plug of cotton wool in the top. And that part's important because it lets the gas out but stops any of your liquid from splashing out and messing up your reading. You put the whole thing on a digital balance, and then you just sit back and record how the mass changes over time.
Now our second method kind of flips the script. Instead of looking at what we've lost, we're going to measure what we've gained. We're going to actually collect the product, the gas, and measure how much of it we have.
So the setup here is a little bit different. You've got your flask, but this time it's sealed, and attached to a little sidearm is a gas syringe. As the reaction chugs along and makes gas, that gas has nowhere to go but into the syringe, pushing the plunger out. All you have to do is write down the volume on the syringe every minute or so. Easy.
Okay, so we've run our experiment, and now we've just got a list of numbers, mass at different times or volume at different times. That's great, but how do we make sense of it? Well, we draw a graph. This is where the raw data turns into a story, a visual story of our reaction.
So let's imagine we did that mass loss experiment. Our data might look something like this. At time 0, we started with 25 grams. A second later, it's down to 23.2, and it just keeps dropping. These little data points are going to form the backbone of our visual story.
And here it is. This is the single most important idea of this whole explainer. When we plot that data, the steepness of the line, what mathematicians call the gradient, is the rate of the reaction. Let me say that again because it's huge. The steepness of the line literally tells you the speed of the reaction. A really steep line means a really fast reaction. A shallow line means a slow one.
Let's look at our graph. Right at the very beginning, at point A, look at how steep that curve is. It's practically a nosedive. That tells us, without a doubt, that the reaction is going at its absolute fastest right at the start.
So, why? Why is it faster then? Well, it's all about concentration. Think of it like a packed party at the very beginning. The flask is crowded with reactant particles all bumping into each other. The more particles there are, the more collisions you get, and the more reactions happen. So, highest concentration means the fastest rate.
Okay, now let's move along the graph to point B. You can see the curve is starting to flatten out, right? The gradient isn't nearly as steep,
That's our visual cue that the reaction is slowing down. Why? Well, our reactants are getting used up. The party is thinning out. Fewer particles means fewer collisions, and that means a slower reaction rate.
And finally, we get to point C. The line here is totally flat. A flat line has a gradient of 0. What does that mean? It means the rate is 0. The reaction is over. It stopped. One of our reactants has been completely used up, so there's nothing left to react. The party's over.
Now, these gas measuring methods are awesome, but what if your reaction doesn't make any gas? What do you do then? Do we just throw our hands up and guess? No way. Chemists have a few more tricks they can use.
Really, the key is to track any change you can see or measure. For instance, maybe a reaction creates a beautiful deep color. We can use a special instrument to measure exactly how fast that color gets more intense. Or sometimes two clear liquids mix and form a cloudy solid. We call that a precipitate. We could put a cross under the beaker and time how long it takes for the solution to get so cloudy that we can't see the cross anymore. The specific technique might change, but the principle is exactly the same. Measure a change over a period of time.
So, okay, we can measure reaction rates in a lab. Great. But why does this actually matter? Well, as it turns out, being able to control the speed of reactions is totally fundamental to everything from making money in industry to literally keeping people safe.
Let's talk about safety first. Fine coal dust in a mine has a massive surface area. That means it can react with oxygen in the air explosively fast. Understanding that rate is what allows us to design safety measures that prevent horrific explosions. It's a life or death calculation. And then on the economic side, nearly every industry you can think of uses catalysts to speed up reactions, letting them make their products way faster and way cheaper, which saves them time, energy, and billions of dollars.
And that really sums it all up, doesn't it? Sometimes our job is to slam on the brakes on a dangerously fast reaction to save lives. And other times, our job is to stomp on the accelerator of a slow but really useful reaction to make our industries more efficient. It is all about control.
So, we've seen how scientists measure and control reaction rates for safety and for profit, but this stuff applies to all of us every single day. Just think about it for a second. When you put your leftovers in the fridge, what are you doing? You're slowing down the rate of the chemical reactions that make food go bad. When you turn up the heat on the stove to cook dinner faster, you're speeding up those cooking reactions. So my final question to you is this. Where else in your daily life are you secretly a chemist, controlling reaction rates without even realizing it? Think about it. Thanks for joining me.